So this one is a structure pop quiz 30. You can mention your doubts if you have. Question number one, any doubt? One part A. Question one, part B, any doubt? Question one, part B. Write equation for a reaction of NaCl and PCl5 with water. Include the state symbols in both equations. So usually, like example, NaCl, it's an ionic compound. When we add ionic compound to water, and most chlorides are soluble except silver, mercury, and lead. So the sodium chloride will dissolve. So if the sodium chloride will dissolve, what will the result? It will form a sodium ion, which will be aqueous, and it will form a chloride ion that is also aqueous. PCl5, phosphorus pentchloride is there because if you compare some of the chlorides are acidic, so when it will mix in water, it will form phosphorus acid and hydrochloric acid. So there's a result for this reaction. Actually, when a sodium chloride is added to water, there is no chemical reaction, it's just a physical change. Like you have a lattice of a sodium chloride, you have a sodium ion and the chloride ion. When you add to water, just ions are separated from each other. It's not a chemical change, it's a physical change there. So that's why for the first one, when NaCl is added to water, it just break down into sodium ion and the chloride ion. But when PCl5 is added, phosphorus pentchloride is added to water, H2O, it will dissolve. And you have to learn these reactions. So whenever we add it to water, H2O, so it will form the acid H3PO4, and acids are aqueous, so this will be AQ, and it will also form a hydrochloric acid HCl, and the aqueous as well. And then we have to balance the equation. So for balancing, we start with oxygen. So if we have four oxygen, so we put four oxygen is balance. Then we balance hydrogen, 3 plus 1, 4 are there, and here we have 8. So 3, we want to make it 8, so we put 5. So this is also balanced. And then chlorine and PCl5, rest all of them are balanced as well. For those who just joined now, this is the structure pop quiz. Question number one, this is discussion. Question one, part C, any doubt? Question 1C. C1 and 2, no doubt. Part D, any doubt? Okay, in part D, 3.3 grams of a sample of a period 3 chloride is heated to 500 Kelvin in a sealed flask. At this temperature, the chloride in the gas has a volume of the chloride is a gas of a volume 250 cm cube, and the pressure in the flask is 323 kilopascal. Use the ideal gas equation PV is equals to nRT to calculate the molar mass of this period 3 chloride, and then we deduce the formula. So first we will use this formula and we have to substitute the values here. That we have PV is equals to nRT. And using PV is equals to nRT, we are finding the moles. And after finding the moles equal mass in gram divided by the molar mass. So if we need the molar mass, so that will be mass in gram divided by the moles. We'll get the molar mass. So we just use the formula PV is equals to nRT, where P is the pressure. If N is our subject, so it will be PV divided by RT is equals to N, where P is a pressure V is the volume of the gas. But keep one thing in mind, the unit conversion is important for this equation. The unit is very important. The base unit of the volume should be in meter cube. Okay. The pressure should be in Pascal. The temperature should be in Kelvin. So we have 323 kilopascal. So we can write 323. So we multiply by 1000 or kilo, the prefix for kilo is there. So it means 10 power 3. Then the volume is there 250 cm cube. If we have 250 cm cube, we want to convert into meter cube. If we want to convert the centimeter into meter, what we do? We divide it by 100. But we want a centimeter cube to meter cube. So what we do? We divide it by 100 cube. So this will be divided by 100 cube. So we can say 250 divided by 100 cube, or 250 into 10 power negative 6, because 100 cube will be there. So we just divide. So we can also write 10 power negative 6, or you can solve, just divide there, divided by the general gas constant, which is 8.31, times the temperature. So temperature should be in Kelvin. It's already in Kelvin, so we don't have to convert the unit. When we simplify this, we'll get the number of the moles. How many moles are there? So we got 0.0194 moles. Okay. So these are the moles. Then we need the molar mass. If we need the molar mass is mass in gram divided by the number of the moles. So this was 3.3 and divided by this value, which is 0.0194. So we got 100 and how to convert Kelvin is already, it's already in Kelvin, but what if it was in Celsius? So then to convert into Kelvin, what we do, we add 273. If it was in Celsius, then we add 273 to convert into Kelvin. So 3.3 divided by 0.0194. What's the answer for this? So 170, 169.8, okay. Okay. Now we have this. Now we want to determine which chloride is this. Formula of the period 3 chloride. So which chloride is having the mass of 170? You check the table here. These are the chlorides of the third period. So if it was a sodium chloride, let's say it was a sodium chloride, then what will the formula mass? The formula mass will be 23 plus 35.5. So it will be 58.5. So it means it cannot be sodium. If it was aluminium, then it will be 27 plus 35.5 times 3. If it was silicon, silicon is 28 and chlorine is 35.5 multiplied by 4. So 35, this will be 71 plus 142, and 142 plus, like this is 142 plus 28. So the sum will be equals to 170. So the answer, it will be silicon chloride. In part E, any doubt? E1 and 2? E1 and 2? E2? An excess of a chloride ion is added to bromine. Describe what is observed. Okay. Yeah, I will discuss both parts. E1, as you see, remember the more reactive halogen displaces a less reactive halogen ion from its So as a result, it's already, we have a chloride ion. Chlorine is more reactive and bromine is there, which is less reactive. It's a molecule. So an excess of a chloride or aqueous chloride is added to bromine. Will they react? So already it's a bromine is there. So there's no reaction between them. If it was a chlorine and we were having a aqueous bromide ion in the solution, yes, they will react, because always that what is the tendency of the more reactive, even a metal or a non-metal, they have a tendency to turn into an ion. The more reactive metal has a tendency to turn into ion. For a metal, it will form a positive ion, and for non-metals, it will form a negative ion. So in this case, when we are adding an aqueous, like chloride ion is added to bromine, so because they won't react with each other, so the appearance of the bromine will not change. Bromine is already orange in color, so the solution remain orange. And what is the color of this chloride ion? These halide ions, their solutions, they all are colorless, like chloride ion, bromide ion, iodide. The solutions are all colorless. So if I add a colorless substance to an orange substance and the reaction is not taking place, so what will happen? It will remain orange. It won't change a color. And explain your answer. So what is the reason for that? We will mention because the bromine molecule cannot oxidize the chloride ion. Bromine is less reactive. So the bromine molecule cannot oxidize the chloride ion. Or we can also say chloride ion. Chlorine is more reactive, so it has already an ion, so the further reaction will not take place. Is it clear? E1? Uh, does saying nothing new is observed? Yeah, it is also fine. If you say no visible change is there, that is fine. Yeah, sure, I will explain again. See, in the solution, in a container, we have a container, and the container is actually filled with a bromine. What is the appearance of the bromine? Aqueous is written. So what is the appearance of aqueous bromine? Aqueous bromine is orange in color. So one of the student mentioned, can we write a higher, greater tendency to be an ionic form? Yes, you can mention, but more scientific, like more appropriate answer is you use the term oxidation or reduction or oxidize or reduce. That's the best term you use when you support that they are reacting or not reacting. In this, we are adding an aqueous chloride, like chlorine solution is added. What is the color of the chlorine solution? It is colorless, the chloride ion. So when you add this, the reaction will not occur. Why the reaction will not occur? Because when you have a chloride ion and you're reacting with bromine, when we compare, the chloride ion is already present as an ion and a bromine molecule is there. The idea is that the more reactive halogen displaces the less reactive halogen from its compound. So if you have a fluorine, chlorine, bromine, and iodine, these molecules, so the tendency to oxidize the other, it decreases as we go down. So the bromine does not have a tendency to oxidize this chlorine and form a chloride ion to form a chlorine molecule. That is why there will be no reaction happen or occur. If there is no reaction happen or occur and I'm adding a colorless substance to an orange substance, so what is the appearance of the mixture? The appearance of the mixture won't change. As there is no reaction, so as a result, it will remain orange. So one mark you will mention the color will not change, it remain or no visible change is acceptable. And the second point you will mention that because the bromine cannot oxidize the chloride ion, it is not a good oxidizing agent. That's why the reaction does not occur. So always the more reactive can displaces the less reactive. The more reactive element displaces the less reactive ion from the solution. But already chloride is more reactive, it is stable. That's why the reaction does not proceed. The next is related to intermolecular force. Sulfur dichloride, which has a relative molar mass of 103.1, it is a liquid at room temperature. Sulfur dibromide, which has a molar mass of 119.9, is a gas at room temperature. explain the difference in the physical state of SCl2 and SBr2 and give your answer in terms of intermolecular force. First thing, because they will have a difference in the electronegativity. So whenever they have a difference in electronegativity, they will have a dipole-dipole force. Like we will have a sulfur dichloride. Sulfur will have two lone pairs and two bond pairs. This will be, as we move across the period, the electronegativity increases. So this will be partial negative, this will be partial positive. And there will be another molecule of the sulfur dichloride. So partial negative and partial positive. So this will attract, there will be attraction between the dipoles. So when there is attraction between the dipoles, what we call that as a dipole-dipole force. That is one thing. Okay. And the second force, which is always there, it is irrespective of the type of a compound or a molecule. Yeah, so there are dipole-dipole force or a permanent dipole, and there's also dipole-induced dipole force. Why dipole-induced dipole? It's always there, irrespective of the nature of a compound. Dipole-induced dipole force is always there. When we compare, when we compare sulfur dibromide, they mention it is a gas. So bromine is there, the bromine is there, and then this will be partial positive, partial negative, partial positive, partial negative. Now, there will be attraction between the dipoles. There will be attraction between the dipoles. So because of dipole attraction, dipole, dipole, and because of the number of the electrons or the electrons in the system, they will have dipole-induced dipole. Remember, dipole-induced dipole force depends on the number of electron. When we compare the number of electron, chlorine is having only 17 electron, like one chlorine, but bromine is having more electrons than chlorine. So when we compare the dipole-induced dipole force in sulfur dichloride, the dipole-induced dipole force is smaller as compared to sulfur dibromide, which is having more electrons. So it means it will have a greater dipole-induced dipole. But because of the difference in the electronegativity, between a sulfur and a chlorine, they will have a dipole-induced dipole force. And due to the difference in the electronegativity, there is dipole-dipole force. So due to the difference in the electronegativity, yeah, chlorine is more electronegative. So when chlorine is more electronegative, they will have a stronger dipole-dipole force. This will have weaker dipole-dipole force. So the dipole-dipole force, when you're comparing, you compare the dipole-dipole force. Because if you was comparing dipole-induced dipole force, according to dipole-induced dipole force, this should have a high melting point or a boiling point. And this should have a low melting or a boiling point. But what happened? Because we found, like practically we found that this substance is existing as a liquid at room temperature, this substance is existing as a gas, so which is having a stronger force. So I mean this is having a stronger force and this one is having a weak force. So how we explain that why this is having a stronger force? So the reason is that because of the greater difference in the electronegativity between the sulfur and chlorine, so it has a stronger permanent dipole as compared to SBr2, which is having a smaller difference in electronegativity. So the dipole-dipole force are there, but they are weaker. So collectively, like the total sum of dipole-induced dipole and dipole-dipole will result in a melting point. So the total sum of these two forces is greater in SCl2 as compared to SBr. Got it? Is it clear? So you have to relate. You cannot say only dipole-dipole or you cannot say only dipole-induced dipole. You have to relate these two forces first. Look, in SCl2, stronger dipole-dipole force and weaker dipole-induced dipole. In SBr2, smaller permanent dipole and weaker permanent dipole and stronger dipole-induced dipole. And these the sum of the two forces in SCl2 is greater than SbR2. That's why it has a high melting or a boiling point, or it is liquid at room temperature where other is a gas. And dipole induced dipole force is always there irrespective of the nature. In part F1 and 2, any doubt? F part 2. Bismuth react with the chlorine to form BiCl3. BiCl3 is a solid at room temperature. It melts when heated gently, like we supply a smaller amount of energy and it just break down. BiCl3 react vigorous with the water to form at room temperature to form an acidic solution. Suggest the type of the bonding, the structure shown by BiCl3, and explain your answer. So it is solid at room temperature, but what happened? It just break down by a gentle heating. So what this give an idea? Like it means it has a smaller melting point. So if a smaller melting point, so what this give an idea about the structure? It give an idea that this should be a simple structure. How we get this idea? It has a simple structure, not a giant, because you see this statement, it melts when heated gently. So we just heat it gently and we observe that it has melted. Then it react vigorous with the water at room temperature to form acidic solution. So it means it is breaking down the water. So which type of compounds have a tendency to break down the water? Ionic. If it was an ionic, then it will dissociate into ion. But if it's a covalent, like a bonding is covalent, so what this give an idea that it will cause hydrolysis, because a covalent compound cause hydrolysis of the water molecule, like breakdown, or the water molecule cause a breakdown of these chlorides. When water is used, if it's the same thing, like if you remember, we did PCl5. When PCl5 was added to water, what we were getting, the products, we were getting H3PO4 and we were getting HCl. So this is called hydrolysis when water is a reactant and break down the compound. What this give an indication? This give an indication that this type of a compound is a covalent compound. If it was an ionic compound, then what should happen? The same thing like we wrote NaCl. When NaCl is added to water, the NaCl will dissociate into ion, sodium ion and the chloride ion. This is a physical change. Like it just dissociate and break down into ion. So this property shows it's a covalent, and the first property shows its structure. It is a simple structure. If it was a giant structure, then it should melt at a very high temperature. So a substance to be solid at room temperature does not mean it has a giant structure. Even like example, sulfur is solid at room temperature, but it can easily melt if we supply energy. Is it clear? Question 2, part A, 1 and 2, any doubt? Does forming an acidic or alkaline tell us anything about the bonding of a salt? Yes, it does tell about the nature of a salt if it's forming an acidic or alkaline solution, especially the chlorides. So if it is forming an alkaline solution, it gives an idea that it is amphoteric in nature. Where it is forming an acidic solution, so if the substance break down, if a salt break down, like hydrolysis reaction happen or occur, so this give an idea it's a covalent compound or a bonding is covalent. Next is barium. Next is barium chloride has a melting temperature of 962 degrees centigrade or degree Celsius, and calcium chloride has a melting temperature of, sorry, cesium chloride has a melting temperature of 646. by considering the ions involved, the difference in the melting temperature for these period 6 chlorides. The for the ionic compound, the melting temperature depends on what? It depends on the size of the ions. The size of the ions for a stronger attraction should be small. For both positive and negative, the size should be small. And it also depends on the charge of the ions. The charge of the ions should be large. So when the ions have large charge, means they will have a stronger attraction. So two things we always compare. One is the size, another one is a charge. So first thing when we compare the charge on the ion, the chloride ion is -1 both cases, but a barium is there which belongs to group 2, so 2 plus. Where cesium is there, it is a group 1 element. So what is the charge? The charge will be plus. So first thing, barium ion is having a stronger, like greater charge as compared to the cesium ions. And so size of ion should be small. So this fulfill, like it has a smaller size. It also depends, like it's first the charge of the ion should be large. So barium is having a large charge. We talk about charge. What about the size? If you remember, as we move across the period, what will happen to the size? The size decreases. Like we have a cesium and then we have barium. So what will happen to the size? The size will decrease. So barium will have a smaller size, cesium will have a larger size. So barium is having a smaller size, so smaller size is there and larger charge. So how you score 4 marks? One thing you will mention, barium is having a smaller size than cesium. Second point, you will mention barium is having a greater charge than cesium. So stronger attraction between the ions. So we need lot of energy to break this ionic bond in a lattice. That's how you score 4 mark. 1 mark relating size, 1 mark relating charge, 1 mark mentioning stronger ionic bond, 1 mark for mentioning greater amount of energy is needed to separate the ions from each other. How barium is having a smaller ionic radii, because if you see, when we move across the period, the cesium is losing 1 electron only, whereas barium will lose 2 electron. It's a group 2. And when it loses 2 electron, for the same number of the shells, more protons are there. So there are 55 protons for the cesium and there are 56 protons for a barium. Cesium lose electron, it's a like 1, 2, 3, 4, 5, period 6 is there. So first we'll have 6 shells, but one of them will be lost because it loses. So this will be cesium. And same thing for barium also, 6 will be there, 1, 2, 3, 4, 5, 6. But when it will be lost, one will be lost. As a result, what will happen? Here, 55 protons are attracting the electron from the last cell. Here, 56 protons are attracting electron from the last cell. That's why when we move across, the size what we'll observe it will decrease. So barium will be smaller in size as compared to that of cesium. Is it clear? It's the same idea. Yeah, the fourth mark is a greater energy needed to break the ionic bonds in the lattice. That's the fourth mark. Part 4, any doubt? Part B, any doubt? 4, okay. Covalent and ionic bonding are extremes of the continuum of type of the bonding type. Explain the difference in the bonding between a barium chloride and a beryllium chloride. So the electronegativity is given. Like ionic and covalent bonding are like extreme are there when it depends on the electronegativity difference between the two. When we compare the electronegativity difference, First, we have barium and chlorine. What is the electronegativity difference? So 3 minus 0.9, so they will get electronegativity difference of 2.1. Then beryllium and chlorine, what is the electronegativity difference? Electronegativity difference is 1.5, I mean, not 6. So the electronegativity difference is 1.5. Now, when a compounds are forming, now when a compound is forming an ionic bond, to form an ionic bond, there's a specific difference is there in a electronegativity, which is, so for a complete ionic bond, whenever they, how the statement is, no, covalent and ionic bonding are extreme. So explain the difference in the bonding between a barium chloride and a beryllium chloride. So using the electronegativity difference, we can work out whether the bond is ionic or it is a covalent. So if we have electronegativity, usually we can say it's about 1.7 or greater than 2.1, we can say if it is the electronegativity difference is greater than 2.1, what will be the type of a bonding? It will be ionic. 1.7 is usually the refer, but it's fine. 2.1 you can remember. But if we have an electronegativity difference which is less than 2.1, so what will the nature? The nature of a bond will be a, no, it's not a rule that the if it's a metal and a non-metal, it will always be ionic. It depends on the difference in the electronegativity. So it's not ionic. It's if you see a metal, you cannot directly say it's an ionic. It can be covalent as well. So when you take the electronegativity difference, it was 2.1, but when you take a electronegativity difference, it is 1.5. So if the electronegativity difference is like greater than 2.1, it will be ionic. But the electronegativity difference is less, usually like less than 2.1, it will be covalent. So what kind of bonding beryllium chloride will have? It will have covalent. And what kind of covalent? Because a covalent is of two types. So how we know whether a bond will be a polar or a non-polar? So a polar covalent when it is ranging from 0.5 to 2.1. And if it is less than 0.5, then it will be a non-polar. Is it clear? So we relate here, we'll say in a barium chloride, the electronegativity difference is 2.1. So it shows it should be ionic, large difference in electronegativity, where beryllium chloride, the electronegativity difference is 1.5. So it will be a covalent. And what kind of covalent? It will be a polar covalent. If it is less than zero point 0.5, then it will be a non-polar covalent. Is it clear about the type of bonding? How you will get the mark? You will refer the difference. You will say in beryllium chloride, the electronegativity difference is 1.5, where barium chloride, it's 2.1. So barium chloride is more ionic and it is less covalent, where, or you can say, and same thing for beryllium chloride, it is more covalent, less ionic. Part B, any doubt? The calculation. A solution is made by dissolving 7.98 grams of group 1 sulfate. No doubt in this? Okay. So this was a pop quiz 13.